always familiar to all of us, which is the Solvay conference held in 1927. In fact, 17 of these people got Nobel Prize in the following years, which is why this picture became so famous. Now, there is a difference between this picture and the original photograph. The original photograph was in black and white, whereas this is a color version. And of course, this artistic skill, which enabled the artist to convert this black and white image into color, is really admirable. But my point is different. I just want to ask whether a machine be intelligent enough to color the photograph appropriately. It's because this is an old photograph. And to know where to put the particular color, the machine has to understand how the grayscale tints are related to the actual color of the surface. Maybe it's a skin, it's a cloth, it's a walls, etc. There's an additional problem. If I want to train a machine using the traditional method, I need a training data set. And in this particular case, it is very difficult because none of these people are alive. And the scene has to be, the scene has changed over the past 100 years. So it's very difficult to imagine how the painting has to be done by a machine. But let us ask the question, how would a human painter do it? Definitely we know the answer. A human painter would look at available black and white photographs and will try to understand how the tints are related to their colors. You also know that a leaf might look green while a human never looks green in color. That is what we mean by understanding. A context-based knowledge about the topic. So the question is, can we generate this context-based awareness or context-based knowledge in the machine? Consider a totally different scenario in which suppose you are a fashion designer. How would you learn? You would learn to understand what fashion is. Fashion is a term which does not mean anything. It's a concept. It is a mental makeup that what fashion is. So how to understand what fashion is, what you will do is you will go to different sources, read different books which deals with the different fashion clothes, with fashion dresses, etc. And suppose a machine has to understand this. And if it can understand, it should be able to generate fashion goods for you. In fact, this has been possible. And what you see here are all fashion goods generated by the machine. None of them are real. They are just fabricated by the machine by understanding, by looking at a large database of different fashion clothes, fashion wares, and just imagining how the object should look if it should be appealing to the person who is looking at it. So let's ask the question, what is understanding? So I'm putting forward some postulates here which may be debated but are for the sake of the presentation now. Knowledge helps us to identify things. So I know that in each of these columns, any of the objects that I see are of a particular type because I have learned how to classify them. So classification was the job of traditional machine learning tools, where I would ask the machine to classify a particular kind of object into a particular group and then tell me what it is. So classification, for that, the machine needs knowledge. But understanding is one step ahead. It helps to create new entities based on existing knowledge. And that is where I argue that machines have started to understand things. They are able to understand scenarios and are able to create new entities based on existing knowledge. It's Of course, behind or one step behind, or maybe multiple steps behind what we mean by intelligence. Intelligence may be defined as the ability to create new knowledge from acquired knowledge. So these are just three postulates that I put forward, and maybe we can discuss it as we proceed. Now, if you are not impressed by the quality of the images in the fashion goods, here are some beautiful faces. And I must tell you that none of them are real. They are fake images created by machines based on acquired knowledge of faces. See how realistic they look. And that is because machines have started to understand what we mean by attractive face, what we mean by fashion, what we mean by the face of a girl, what we mean by the face of a boy. In fact, there are systems which will be able to generate according to your specification. If you say that the person should have a gray hair, it will give it a gray hair. If you say that the person should smile like this, he or she would smile that way. So all these things are now possible because machines have started to understand the scenario or the language in which we try to communicate with them. Now, looking at the history, a perspective of the historic development of artificial intelligence, it can be divided into different epochs. And if you consider the period prior to 1986, we may call it the early ages, where machines were just being tried to, machines were just programmed to do tasks as we want. But in 1986, there was this backpropagation algorithm which came up, which gave way to feature-based learning. What it means is that if you have a set of features that can be used to classify a set of objects, then these machines are able to learn by themselves how to separate them into different classes and tell you which belongs to which class. Just to illustrate what I mean by a feature, look at this picture. The face of this monkey, this is a Chinese monkey, it looks very much like a human. But the machine will immediately say that this is a monkey, not a human, because it has a tail. So tail is the distinctive feature here, which helps the machine to separate this picture from the picture of humans or vice versa. Now, feature-based learning, after feature-based learning, we came to data-driven learning, which in fact took its root in by about 2006, when a lot of data started coming in. And Google, for example, is a very good example for data-driven learning. If you ask Google a question, most of the time it gives you an intelligent result. And this is by doing an intensive search through the database. So Google has big machines which are able to do these things, and that is how it is possible. And latest in the series is the understanding models, and it's a name that I coined here. I have not seen it used anywhere else. But these are pseudo-intelligent machines. What they do is that they are trying to understand the scenario and trying to develop new things based on their understanding. So this is the area of research that we are mostly focusing here. And I have research students like Robin, for example, who has joined this meeting, who is working on a particular type of neural network machine learning tool, artificial intelligence tool, which is called the GAN. And for today's talk, I am also focusing on the same thing, GAN. I'll tell you what GAN is, but let us just go slowly. This is a traditional learning scenario where you have an instructor who helps the learner, the child here, to understand what she is trying to understand. So the learner is the human here, who is a human instructor. And if I replace this child with a machine, That is what traditional machine learning was all about. You still needed a human instructor to tell the machine what to do, how to pick up the features, and what features are to be used for classification, and what are the labels that are to be provided. But if I replace the human instructor with a machine instructor, and the human learner also with a machine, then what I get is the GAN, or the Generative Adversarial Network. And GAN is a very powerful and general model which has many variants that are available. And I'll be going through just one of them, one or two of them, which we have been using recently. So in machine learning, the machine instructor is called a discriminator, and the learner is called a generator. There are some minor differences between the instructor and the learner here, which we'll see as we proceed. Now, if you look at this learner and the discriminator or the instructor, I must say that the discriminator is a highly knowledgeable entity or a highly knowledgeable machine about the problem domain. It has been trained specifically for some problems, and it knows at least how to say whether something is right or wrong. And the learner, as usual, or the generator, is a completely ignorant machine which has no idea about the problem domain. And our goal, or the goal of the discriminator or the instructor, is to teach the generator how to learn a problem or how to learn a scenario based on the instructions that it gives. The important point here is that the instructor is taking the place of the human who used to teach the machine in the earlier scenarios. So let us come back to the phases. We can use GAN for generating phases, and in fact, all these phases were generated using the GAN. And how can this be done? Let us look at it. As always, what we need is a training data. A child recognizes face by seeing people who have different faces, and the child realizes who is who by identifying specific features. But the child is never told how to separate, how to distinguish a person from another. It's only shown the faces, or it's only shown the people. Now, likewise, here also we have a large data set of celebrities, because we are looking for beautiful men and women. We are going to celebrities database, which contains about 200,000 celebrity images. So the instructor or our discriminator is trained on this data set. And we also provide some random drawings which the instructor or the machine uses, the discriminator uses, to say that they are not the faces it is looking for. So that is what we do. Train the discriminator to distinguish between real faces and random drawings. And real faces we have in the database, and random faces, of course, these random faces are much better than what I mean by random faces. They could just be drawings here and there. And once the training is over, the discriminator is clearly able to say which of them is real and which is fake. That is the first step. Now what we do is that since we have a machine which is now able to say which of them is real and which is fake, just yes and no answer, a binary answer. In fact, along with that binary answer, it will also provide a metric which is used by the generator to learn. Just like we give hints to students when we teach them. So the discriminator, what it does is only to say which image is real and which image is fake. Now the generator As I mentioned, it has no idea what the situation is, but it has a canvas on which it can draw. And just like a child who is not able to understand anything draws some random curves, the generator draws some random curves and submit it to the discriminator. The discriminator immediately finds that they are fake images and returns a message to the generator saying that, sorry, these are not the real images I am looking for. But in addition to telling the generator that the image it has made is fake, the discriminator also returns a metric on how much the image differs from reality. So this information is used by the generator internally to train itself, to update itself, and make some more intelligently, I mean, intelligent means some more better images of the celebrities with its database. So the generator updates with information received from the discriminator and returns a new image, the updated image, back to the discriminator. Of course, the discriminator finds that it is not up to the mark, so it will message back to the generator that it is not what it wanted. This process continues. This process continues until the images generated become indistinguishable from the real image, which means that just as the case that I show here, the fake images looks very much real. So this is how these fake images are created, and this is an active area of research. Now, the important point is that once this learning is over, we don't need the discriminator anymore. The generator can keep on generating new images of people which are not real, fake faces of this kind and of high quality. Now that is about image generation. Now the question is, can we take it to do some scientific research, scientific application? Can we find some scientific application where this can be used? And I'll explain two scenarios in which we have been using it in astronomy. So what I'm going to discuss now are two scientific projects that we have been doing and which are nearing completion at ARIS 40. As you know, telescopes have extended our visibility to the farthest edges of the universe. However, when we are observing from Earth, the greatest hindrance to our visibility is the atmosphere, and it scatters the light randomly as it reaches. And this is why the stars appear to twinkle at night. The light beam that is coming towards us gets deviated in different directions, that its brightness keeps on increasing and decreasing depending upon how much of the light is coming to our eyes. And because most of the celestial bodies are very far away, they appear like point sources in sky, and the wavefront that is coming from are mostly parallel wavefronts until they reach the atmosphere of Earth. As soon as it reaches the atmosphere of Earth, because of the random fluctuations in the air, the dynamics, it gets distorted. And this distortion, which in the ideal case would have given us a point as a point source, would give a highly distorted, aberrated wavefront, producing an aberrated or a distorted image. So the kind of distortion depends upon how much turbulent the atmosphere is. But because this is a random process, we can always assume that whatever will be the result, it is going to be a Gaussian profile that it produces. Now, It's practically impossible to track back a Gaussian process to say which beam of light got deviated and which beam is coming straight. What I illustrate by the central limit theorem, which tells us that this will produce a Gaussian distribution, also says this same point. We can say that a particular ball here has come from this location, but what is the track that it has taken for coming here? That's not clear to us. So this is the challenge, and we want to set it correct and see whether this can be done with reasonable quality without distortion. Now there are two possible solutions. Since we know that the distribution is Gaussian, we can deconvolve the image with a point spread function, PSF, to get back the original. And that is a traditional method that astronomers have been using for a long time. They look for the known stars in the sky, check how much it got distorted, and use this information to calibrate all other news sources. And for a small interval of time, they assume that the sky is stable. In fact, the sky is highly dynamic. It is not stable even for more than 10 milliseconds. So modern method for doing it uses adaptive optics. So what in adaptive optics they do is they correct the wavefront even before the image is created. This is a highly expensive and computation intensive task. We are proposing two solutions for each of these problems, and that is going to be the topic of today's presentation. Now, this is a project that has been on for last 2 years or more. This is a Indo-US bilateral collaboration funded by the Indo-US Science and Technology Foundation, USSTF. Professor Ajit Kambave, he is from Ayuka Pune, is the principal investigator, and Ashish Mahabal from Caltech and myself are the co-investigators of this project. Kaushal Sharma was a postdoc at Ayuka, is now at Nainital, and he is the person who has been doing the astronomy part, and I am mostly involved in the machine learning part of this project. So this is called PRAGAL, meaning Pan Astronomical Deep Learning Center. So that is where this particular deconvolution GAN or deco-GAN was developed. Now, let me try to explain this situation a little more by telling you what it is going to do. So the question that one would ask is how it works. Well, we have the ground-based observatory. This is the Palomar Observatory in San Diego, California, USA. And we also have space-based observatories. Of course, one or more. In optical, we have one, which is the Hubble Space Telescope. And in other bands also we have. Even astrostat is there. Yeah, our own. Now, what we are trying to do is, at Palomar, this is a 1.2 meter skin telescope. We have a 6 by 6 kilobyte CCD camera to do a full scan of the northern visible sky every night. The major objective of this survey is to find transients or variable stars, and that is called the CTF survey. So the CTF is housed in this Palomar Observatory, and it looks for variables like supernovae, variable stars, binaries, AGNs, quasars, asteroids, etc. And we also have this Hubble Space Telescope, which is a 2.4 meter telescope in space. It was launched in 1990 on the Space Shuttle Discovery. And it is sending us a lot of data. In fact, 150 gigabytes of data every week. So from 1990, it has sent us a lot of data that we can use. Now, the idea is to have these two databases to teach the machine how to handle this variability in the sky in a very transparent, seamless way. The ground-based images are convolved versions of the images Hubble is able to see. So the convolution is done by the point spread function, which I mentioned earlier, which is happening because of the turbulence in the atmosphere. We have database telling us what are the possible PSF values that are seen in the sky at Palomar. And this information can be used to convert the data that Hubble has produced so that it mimics the data that the observatory is actually seeing. But there is an issue here. The point spread function, because it is a dependent variable on the dynamics of the sky, it is not a constant. It keeps on changing with time. And as I mentioned, it is stable only for about 10 milliseconds. It's a small, very small fraction of the time. But traditionally, astronomers estimate the field PSF at any time using standard stars, as I mentioned before, and used it as the standard gauge for calibrating all of the stars. Okay, this is a very laborious process, and we would like to have the GAN take away the burden of this hardship that is usually around the traditional method. So the procedure is as follows. We take a large sample of Hubble Space Telescope images, then convolve it with the wide range of CTF or the Palomar Observatory PSF functions. Then train the discriminator to say which is a space telescope image corresponding to the convolved images it produces. That means this is the target or the image taken by the Hubble Space Telescope, one frame, and we have the image seen by the observatory. As you can see, it is much blurred compared to the other images shot. The point sources have spread out. And what we would like to do is we would like to see how this convolved or blurred image can be converted into that high resolution image which Hubble is able to see. And for an illustration, I am showing you how the convolved image looks at different values of PSF. This particular image is at PSF equal to 5. If I reduce the PSF to say 3, then the image has become slightly better, sharp. If I reduce it to say 1.5, then it is still blurred, but much sharper than before. If I keep on doing it to lower values, then the sharpness keep on increasing. As you can see, 0.8, 0.5, likewise, it will increase the sharpness. Now, I train my discriminator on all these data set, about 1,000 of them, even more than that, but I pick up a small fraction of it and train on them for thousands of images, so that the discriminator is supposed to say only one thing. The discriminator has to say whether it's a telescope image or whether it is a ground-based image. Ground-based image is blurred, so it should be easy for the discriminator to say whether it is a telescope image, I mean space telescope image, or whether it is a ground-based image. Now, once I have trained my discriminator how to separate these two, how to distinguish these two, there are standard methods for doing that. And once I am able to have the discriminator separate the objects into groups which are of ground-based images and of satellite-based images. I am ready to teach my generator how to work. So what I do is that I take the convolved image, which is the ground-based image, transfer it to a small dimensional space, which I call the latent space, and reconstruct the original. In this particular case, try to reconstruct the satellite image from it. So this transformation involves a lot of learning, a lot of computational power, but this is the learning that the generator has to do. And the discriminator, what it does is, it will look what the generator produces at every instant and says whether the image is good or not. If it says no, the generator goes back, checks some of its internal parameters, brings forth a new image, shows it to the discriminator, and see whether it gets passed or not. And this process is repeated for hours, days together, until the generator is able to convert all the images of the ground-based telescope into something that looks very much similar to the space-based image. At this point, the generator is not trained for a particular data set. That is an important point. That's why I call it understanding. At this point, the generator can say, take up any image and convert it into the satellite image, which are on the same range of the training data. Now, one important point here is that there is no human involvement in the process. The generator has to understand what it has to do based on the information given by the discriminator. And that is what the GAN understands, or we claim that the GAN understands what it is doing. Now, to use it for scientific application, it is not sufficient that the images look as good as the space image. It has to be scientifically consistent. So we use a metric to evaluate the quality of the data that it produces. So for scientific data, it is not sufficient that the images look similar as the space telescope images. They should instead preserve the properties of the original space image. Two things are to be observed here. We know that it is a Gaussian process. So the effect on the star would be to spread out the light accordingly. So the process that we do here should be able to reconstruct the Gaussian effect as shown here. It should be able to reconstruct the effect of the Gaussian process, meaning that the profile should become sharper, or mathematically we would say the FWHM, or the full width at half maximum, should grow small, because when it goes sharper, this width will come decreasing. So that is one criteria. So that should happen. If that happens, what we can claim is that it has gathered the pixel from its surrounding and has accumulated them to reconstruct the image. Now, we also has mentioned that this is a Gaussian process. And if you look at this illustration here, you find that all the balls that are in that basket are coming from the same source. So what it tells us that, although some of them are thrown out, the fraction of the photons that I collect in my profile should be the same that was distributed earlier. So all the distributed pixels have to be brought together. And this is what we do when we say that the photometry is correct. What we mean when we say that the photometry is correct. So that also has to be verified. So these two tests have to be passed for the particular application to be scientifically useful. So this is what we get. It shows the decon performance. At PSF5, we have the deconvolved image. And this is the prediction or the reconstructed image. And this is a Hubble Space Telescope image. Visually, they look very identical, except perhaps for this one, there is a small tail-like structure. There is nothing here. Other objects almost look similar, which means that visually, these two images look similar. And if I change the PSF to 3, this is how the prediction looks. Again, it is very much similar to the Hubble Space Satellite Telescope image. If I change the PSF to 1.5, again I see that the stability of the network is established. So in all these cases, the decon output looks very similar to the Space Telescope image, which means that visually the method is working. Now this is how it would look if I plot all the PSF values. On the left-hand side, I have all the PSF values. So this is PSF5, PSF3, 1.5, 0.8, 0.5, and 0.1. And on the right-hand side, I have the reconstructed images. You see that though this change is very large, the changes here are minor or is not at all relevant for most of the studies. In other words, this was a hard job that astronomers have been doing so far. Now there is no need to go and find out the PSF of the standard star as we did in the previous cases, the traditional. We have the machine which is able to handle the different PSF and give us reliable output. But we are not done yet, because we need to show that the photometry is also correct. For that, there are tools like IRA, for example, which is able to look at the profile of the particular objects. I show here 2 objects which are shown in green circles. And I also show the corresponding flux values for each of them. So you find that this is the flux 10497, 10726, 10846, 111111. Okay, you find that almost all of them are close. The small variation is because of the photons that are thrown out during the Gaussian process. But the machine has in fact conserved the total flux within the star. So we can now measure the flux of the star irrespective of the sky disturbance we have, which is a huge advantage for traditional astronomical methods. And for the second case also, we see that the same thing is the values are stable or constant within limits that are acceptable. Okay. Now, one may ask, if we can reproduce the results Hubble Space Telescope was able to do in space with ground-based telescopes, does it mean that we need not have to invest huge money on space missions anymore? A very pertinent question. The answer is a big no. I'll illustrate why. If you go to a village and look at the sky at night, you find more stars than that's what you would see if you do the same from the town. Why is it so? Because in the town you have a lot of street lights which light the sky, and anything that is fainter than the sky you are not able to see. You have seen the Gaussian process. The spreading goes to an extent where the sky surface brightness equals to the brightness of the star. Then it becomes invisible. And no method can extract the star from that kind of a scenario. So it is not possible to go beyond the limit of the sky. Or one would say, sky is the limit. And interestingly, fortunately or unfortunately, astronomers are more interested in faint objects than in bright stars, because that is where the real science exists. But that said, nevertheless, we could successfully develop a machine that could understand the logic for removing atmospheric distortions produced on ground-based telescope intuitively, rather than explicitly teaching it how to analytically solve it. It is faster and more reliable because the PSF is a floating value, and having a method that can take care of the PSF variations in the sky, which happens in every 10 milliseconds, is a huge advantage for astronomy. In contrast to AI models, we don't need to provide the logic nor the features to the machine in this case. That is why it is said to have intuitively understood the contrast like we humans do. Now I'll briefly, in the next few minutes, tell you another complex problem which we have been trying to address. This is an adaptive optics which I mentioned. It's, it leads to a more complex understanding of what we mean by understanding. That is the AOGAN. This is a joint project in which Professor Ram Prakash from IUCAA, who is also the team leader from India for the 30-meter telescope, which is being built at Hawaii, which is going to be an adaptive optics machine. And most of these technology is developed in India. And we also have Avinash Surendran, who is from the Keck Observatory, which is having a adaptive optics, which is having a telescope which uses adaptive optics. He is a postdoc at Keck Observatory. And Saurabh is a research student at IUCAA. He completed his BTech from IIT Delhi and has joined IUCAA. He's in fact writing his thesis now. He's working in adaptive optics. And I was involved in the development of this particular AOGAN tool. We are just in the development process, and this is an ongoing process in the initial stages. But the results are good, which is why I thought I would present it. So what is AOGAN? As I said, the night sky is impressive with twinkling stars, but not for the astronaut. He is all the more worried about the distortions in the images he gets due to the distorted wavefronts created by the atmosphere. And as I said, the plane wavefronts have been distorted very, very randomly by the atmosphere, that the aberrations it produces, we can at best say that it gives us a Gaussian profile. It's not possible to correct it completely without the adaptive optics, which we are going to discuss. Now, why this is so? It is because, in fact, the problem arises because we use perfect mirrors to focus the distorted wave. So the solution is there. if we distort the mirrors in such a way that it is matching to the wavefront distortions, then we have the solution. We have adaptivities. And that will solve the problem. Very simple. Easily said than done. Because it has to be done at a high speed, and the process that is going on in the atmosphere is a random process, not completely random. It has, as I said, it has a stability for 10 milliseconds, and depending upon the wind, there is a shifting, which also can be, to some extent, learned and understood. But it varies. So we have to create the mirrors deformed in every 10 milliseconds so that we may get the correct image, if at all we are able to do that. So that is a nearly impossible goal, and which is the reason why adaptive optics is also in its developing stage these days. We have developed, in fact, this mirror has been there for some time now, a technology for adaptive optic system, which is a deformable mirror. And what is seen here is a deformable mirror. Each of those inner hexa shades that you see are mirrors which can independently move so that it can correct for the distortions in the wavefront. And how it is to be moved has to be fed back by a feedback system which corrects for the atmospheric distortion. So in the final system, what you have in an adaptive optics is you have the distorted wavefronts that is coming in. It falls on the deformable mirror, which is deformed by a feedback circuit, which makes sure that the images are coherent, or the wavefronts are coherent, or are just straight lines or plane wavefronts as we design. And if we are able to do that, we get a very sharp image as we see here, instead of this blurred image that we get in a traditional way. Now, how we do it? Well, we do it by shooting a laser beam that gets reflected back from the upper atmosphere and is captured by the second telescope or the same telescope. Since we know how the laser beam should look like, because we created it in the telescope, we can say that any distortion we see there, any variations we see there from the expected final image is due to the atmosphere. And this information can be used to deform the mirrors in the AO system. However, these corrections are computationally intensive, that very huge high-performing computers are required to do it in real time. I mean, within the 10 milliseconds time slot that is available. So this is the real challenge that makes these adaptive optic systems very expensive and difficult to construct. So what is the role of AO-GAN? AO-GAN is a very, very ambitious project to do away with all the high computational demands of adaptive optics. What we'll have is a simple, intelligent artificial intelligence model that understands how to modify the mirrors so as to make plane wavefronts from the distorted wavefronts. It's ambitious, very ambitious, because if we are able to do that, we cut the cost of all the adaptive optics to very small values. Even ordinary telescopes can have adaptive optics. Now, what are the inputs we have? We have the input, which is a distorted wavefront, which is coming from the sky. And as output, we have the correction for the mirrors. Because we have these mirrors there, we need to apply corrections to them. And we have to do the computations from the distorted wavefronts, which is the earliest we can get, and do these corrections on the mirrors so that we get a sharp image. To evaluate the performance of the system, there are some standard methods. And in adaptive optics, the practice is to compute the Snell ratio, which is a measure on how much the spread is happening due to the point spread function. It should have a value of unity if it is a perfect system. And it can be anything less than unity in most of the cases, in all practical situations. In fact, with the best AO available today, it is not more than 2 or 3 decimal places further from the accurate stable in the system. Now, because we do not have a method to directly measure the atmospheric fluctuations, the study has to be done with simulated data. It is possible to simulate the sky very accurately because we know the physics of the atmosphere. Because we are synthesizing the data, it is also possible for us to evaluate the performance of the system based on what is really happening in the sky. So in the movie that I'm going to show you now, I'll show you how the input looks like, which is shown here, and what is a prediction that we have, and what is the ideal situation that is in the atmosphere. If these two are similar, that means we are able to reproduce the conditions correctly. In fact, the difference between the two, which is not visible for the naked eye, is shown here by this tag. Similarly, there are computational methods which takes long time for computation. In fact, about a day for doing this computation, but the predictions here takes less than 10 milliseconds, which is the reason why it is considered to be good for adaptive optics. Now, if we do that kind of computation, then this is the value that you get for the actual, and the actual minus the perfect, that is what is shown. In fact, what you see is that these differences have a maximum value of 0.506. 0.5 is equivalent to 0. So it's a very small fluctuation that is there. Whereas here it is higher, which is in this case. So we are not as good as the ideal system, which is also shown by this Snell ratio. It is stable to the 4th decimal place here, but it is only stable to the 3rd decimal place, very close to the 4th decimal place. So we are not doing better than the highly computational method, but we are very close to it, which is very promising, and this we hope can be further done. And for different inputs, I want to mention another thing. Here also, as in the previous case, we have considered all possible sky dynamics, meaning that from the worst case, which is measured by a ratio, which I don't want to mention here, but from the worst state to the very stable sky, we have varied this output, and you can, as you will see, you can see that it is remaining consistent across all these values. So here we go. You can see that this is stable to the 3rd decimal place. And sometimes it is coming to the 4th decimal place, but mostly stable to the 3rd decimal place. If you look at these images, prediction and perfect, you are hardly able to see any difference between them. The differences are only in the order of 0.01 or 0.02, like that. So, the question is, this is simulation. How does GAN perform on real telescope data? This is the question we would also like to ask and get answered. And hopefully, that shall be the topic for the next talk. Thank you.
Thank you, Ryan and Sajid Philip, for your excellent presentation, starting from very elementary and familiar ideas, building up uh, the foundations of a new discipline, a cross-disciplinary uh, area, which is of great interest and it holds a lot of potential. In fact, enormous potential in the coming years, not only for astronomy and astrophysics, but I think there are applications uh, based on the Earth itself. For example, well, you can monitor phenomena happening on the surface of the Earth. For example, in a part of the city, you can train your machine to simulate and also make predictions, traffic congestions, for example, where to expect the congestion, traffic congestion at what times, and so on. Uh, Such information will be useful in town planning, in traffic planning, and so on. Similarly, for economists, I foresee uh, a lot of scope because at present we don't know in which month the taxes are remitted in large amounts and in uh, which months are the lean months. That means which months for the government to expect large remittance and which months to expect smaller remittances and so on. That is another one aspect of the applications which may be possible. Another area, totally different area, is before the entertainment industry, animation. In fact, Sajid has started saying, making remarks about art uh, is such a way that it is not possible for us to distinguish between genuine art uh, done by humans and fake art done by machines. We can employ machines to produce paintings, sculptures, and so on. So that it will be a make-believe world which we will find difficult to distinguish from the real world. So many applications are in store for uh, this in this area, which is still in its infancy, I think. Okay,
Yes,
I wish all
yes,
the best. I wish all the best to Sajid and his team. Okay, right. You are going to say
yes, sir.
something?
In fact, Robin, whom I mentioned, he is working on space-based images, and he'll be dealing with some of the things that you mentioned, like city planning, where we are able to see, and even mapping of roads. Google Maps, for example, very much use this technique for creating road maps, even in places where it is not very clear to see uh, how the roads go because of the trees or other hindrances. But machines are now able to reconstruct the road maps very clearly, very correctly with this kind of technique. And about animation, Avatar, for example, the movie Avatar was created with some of the techniques that are mentioned here, where the human is replaced by an animal, which looks like a human, but is not real. So these things are being explored worldwide, different areas. And in defense, we are working on a project which will enable people to see intruders even before they are being noticed by the local people. So these kind of applications are very wide and very useful for the community at large.
We would welcome questions from the audience. Sadish? Anybody else? Now for the coordinator, Dr. Srilata, to announce the closure of the program, winding up. Yeah. What next? Srilata? Hello? Srilata? Hello? Srilata is not online? Has left, already left. If the coordinator has left, then it's up to us to stay there. Maybe we can call it today. Thank you. Thanks everyone for your interest.
Thank you, sir.
Thanks. I thank Satish.
Srilata, hello.
Hello.
Sir, ശ്രീലതയുടെ കണക്ഷൻ പോയി, പവർ പോയിരിക്കുക, വൈഫൈ പോയി, അതുകൊണ്ടാണ് ശ്രീലത ഇപ്പൊ എന്നെ വിളിച്ചായിരുന്നു.
Oh, so Dr. Rose Ignatius will say something. We can close the meeting. Okay. We can thank the speaker and the audience.
സർ, അടുത്ത മീറ്റിംഗിൽ ആരാണ് സ്പീക്കർ എന്നൊന്ന് ഡിസൈഡ് ചെയ്യണമെന്ന് ശ്രീലത പറഞ്ഞായിരുന്നു. അടുത്ത മീറ്റിംഗ് ശരിക്ക് സതീഷ് സാറിന് എന്തോ ഇൻകൺവീനിയൻസ് ഉണ്ട്. അതിനടുത്തത് എൻ്റെ ആയിരുന്നു, പക്ഷെ എൻ്റെ മോളുടെ കല്യാണം ആയതുകൊണ്ട് ഐ കനോട്ട് ഡു ഇൻ ഡിസംബർ ആൻഡ് ജാനുവരി.
We will see if somebody is available.